I've been glossing over some really important distinctions. I want to try to address those just a little bit. Okay, so here's a picture, okay? And here's the mass on one side, M1, here's the mass on the other side. And you got the force of gravity on one side, the force of gravity on the other side. So what's the net force on this system? Okay. Now let's be really clear about something that we haven't really emphasized it yet, but the force of gravity is the force exerted between the mass of an object and, at least in this lab, between the mass of the object and the mass of the Earth at the separation of that object from the center of the Earth. Gravity, the force of gravity is a force exerted on a mass. Mass and force are two different things. Okay, force is, well, the gravitational force is just the force exerted on the mass. It's not the same as the mass. And it can get a little confusing because even physicists are starting to say, well, you've got a weight of 10 grams. Well, you can't have a weight of 10 grams. You can have a weight equal to the force exerted by gravity on 10 grams, and that would be 9,800 dynes, or, you know, 0.0098 newtons. I think I got the right number of zeros there. But that's not, the grams aren't a measure of force. Okay, you don't measure force in grams. Okay, well, anyhow, you got the masses and you got the gravitational forces on those masses. Multiply each mass by the acceleration of gravity, and that tells you how much force gravity is exerting on it. Okay, now the arrows here indicate that these forces are vectors. Okay, but there's a little confusion, and I'm not going to address it too much. It looks like you got a vector in the negative y direction here and a vector in the negative y direction here, but those vectors, while they're in the same direction in space, are having opposite effects on this system, because this downward force tends to accelerate the system in the counterclockwise direction, and this in the clockwise direction. Okay, so when I talk about the force vector, there's some ambiguity involved that we need to address as we go through this. So when I write down that the net force is the first gravitational force plus a second gravitational force, it looks like I'm talking about forces in the negative y direction if upward is positive. And maybe I shouldn't have even written that down, because if I want to do this correctly, I've got to talk in terms of torques, but I don't want to define torques when I'm first defining forces. So I'm going to kind of cross that out as something that's probably confusing right now, and just say that your net force is going to be the magnitude of this one minus the magnitude of this one, so that if this one is bigger than this one, the net force is going to be positive, because that's going to accelerate the system in the counterclockwise positive direction. If this one is bigger than this one, then the system is going to accelerate in the counterclockwise, in the clockwise direction, and that would be a negative force. Okay? So I'll just say it's this, because F grav 1 is counterclockwise and F grav 2 is clockwise. And that kind of defines it. So that's a force diagram. Now we're going to do a lot with force diagrams, and we'll start doing that next time. But when we study forces, we'll also feel free to talk about energy changes, since we've introduced the idea and you have a few problems to practice. Just using the idea of kinetic energy and change in 1/2 mv squared, and associating that with the force times displacement product, F delta S, the work done. Okay, well, that's where we're going. So we will, in subsequent video, talk about the idea of work and energy in relation to force, because it's all kind of a natural, a natural little bag of ideas that we want to start using now so that we get good at using them relatively quickly. Okay.